Hello, everyone. Welcome back to the AAS YouTube channel, and this is part of the good stuff. This is the AAS Journal Author Series, and I'm very happy to have Maria Lugaro with us today. Hi, Maria.
Hi, everyone. Nice to be here. Thanks for the invitation.
Yeah, well, thank you so much for being willing to talk about your lovely article there. What's your geolocation, Maria? Where are you at?
So I'm in Hungary, in Budapest.
Budapest.
The capital of Hungary. It's been a nice warm summer, except for today when it's raining and cold. But it's gonna change again.
Yes, that's the one guarantee. I think you have the honor of being actually, no, you're the second person from Hungary that I've done. Yep.
And where are you, Frank?
I am in Phoenix on this August 5th of 2021, and we will be a little bit cooler today. We hit about 43, 44 C yesterday. So it's life in the desert. So it'll be like 40, 41 today. C. So yeah, it's good and toasty. Summer's going well. It's the wet season in Phoenix. This is when we get our rain, is in the summers. But yeah, I'm doing super duper here in Phoenix today. It sounds like you're doing well in Hungary.
Yeah, I just had 4 weeks of holiday.
Lovely.
In Italy.
Oh, you did? Okay.
My family.
Very good.
So that's been great.
Whereabouts in Italy?
In the northwest. So Torino and the Alps up there, the mountains.
Very cool.
Yes.
Very cool.
So I am still relaxed.
Well, may you stay relaxed.
Yes, may I stay relaxed. That's my aim.
So let me ask you a very relaxing question is, what do you like to do for research, Maria?
Yeah, so I like to study nuclear reactions and how they happen inside stars. So mostly nucleosynthesis and mostly the elements heavier than iron. Okay. So elements such as, maybe they have names that people are not very familiar with. I like all these elements because they're called praseodymium or samarium or iridium and selenium. So they're all beautiful, fancy names that people sometimes haven't heard before. So I will mention a few of those when I talk about my paper. And I like, among other things, to have a look if my models of neutron captures can help to interpret what we observe inside stardust grains that we extract from the meteorites. Right. This is not the job I do. I'm saying we as a general scientist term. I am a theoretician, but I rely on people who work in the lab and do all this work. And then they give me numbers. And I try to see if my models can explain what they see in the lab. So that's for me one of the most exciting topics of my research, to looking at these tiny stardust grains. It's actually a speck of a star, effectively, a real physical speck of a star.
Yeah, it's very cool. It's very nice. Awesome. And that is going to bring us to this very lovely APJ article, Origin of Large Meteoritic SiC Stardust Grains in Metal-Rich AGB Stars. And Maria, take us away.
Yes, okay. So I already mentioned what they are, the stardust grains, that they come from meteorites. So there's a lot of keywords in this already. So I mentioned the stardust, the meteorites. SiC means silicon carbide. So these are grains specifically made mostly of carbon and silicon. And I'm talking about large grains because I'm focusing here on grains that have a size about 1 micrometer. These are large, but for this type of grains, this is large because most of them, they have a size about 1/10 of a micrometer, which I think is very interesting to say, because imagine the people in the lab that try to measure what these grains are made of. They need very sophisticated experimental methodology. It's not easy to measure something, what's inside something that is micrometer in size. So
Yeah.
these are very like magician kind of people. Yes, and well, most of these type of Stardust grains, maybe say up to 99%, 95%, not to be too extreme, they come from giant stars on the AGB. So this is why I'm studying them from the point of view of AGB stars. These are asymptotic giant branch stars, where we know that neutron captures happen.
Yes.
And so we see the signature of neutron captures in these elements I was mentioning before, in these strange elements. And we want to see if the models of these stars can match what we see in the grains, basically.
Nice.
If you go up again, because there's something interesting about this paper, I think, is the list of authors.
Indeed.
There are, I think, 17 people on this paper. And the reason is that when we do this kind of work, we have to be very multidisciplinary. So we need nuclear physicists, we need stellar modelers, we need people who analyze meteorites. So we need all of that, and we need in this particular paper, people who are spectroscopy experts. Because in this particular paper, I'm trying to match the grains, not only to the models as people normally do, but also to the stellar observations, which is something that has never been done before, or not so in detail for the heavy elements. Okay. So there are, in these 17 authors here, 4 different types of expertise. And this is the reason why I had to keep on inviting people to help me. See, this is not my job. It's like me and Bori and Blanca and Amanda and Larry, Umberto. Every time I go a step forwards, I'm thinking, I need to ask Claudio what he thinks about this. And so I ended up with this long list of authors, which actually for me is quite usual because I like to ask people for help. And I think it improves what I do and I'm trying to understand. Good, nice, nice. Okay, so I think I set the main topic here already by mentioning that what I'm really trying to do here was something different. Normally, since about 20 years ago, we started looking at the grains because the first measurement, the first single grain measurements arrived maybe 20, 30 years ago. And the first thing we do, we take this measurement, we take the stellar models, and we see if they match. We make a plot with the models and the data, and we see if one stays on top of the other. Yep. And this has been what has been done so far. But what I would like to check, if I can find an observational star, and a star that I observe, which is the counterpart of the composition that I see in the grain, because then I can really tell if they come from that star. And I can avoid all the uncertainties in the models because there is a lot of degeneracy. I can match the data by doing different things. And which one is the right thing? Yeah. So here I wanted to look at observation against observation to be a bit more robust. This is what I was trying to do. Nice. So if you want to go to figure 1, this is why this paper is about Stardust grains, but the first figure is a figure about stars. Yeah. So yes, the first figure is not Stardust. These are stellar data from spectroscopy. Okay. And what we see here, these are barium stars. So barium stars are very interesting because they are binary companions of stars that already evolved on the AGB phase, already produce S-process elements, these heavy elements, and they transfer them on the barium star, so we can see them on the barium star. And the advantage is that the barium stars, they're not as cool as the AGB stars, so it's easier to observe the spectroscopically. Okay. Right? The AGB stars, the original AGB stars, they pulsate they have strong winds, they are cool, they have molecules, and they make dust, the dust that we find in these meteorites. So imagine to try to model the atmospheres of these stars. It's a nightmare, and people do it. Very brave people do it, but often the error bars are like 10, like they give me an indication. But instead, the barium stars, they are hotter. So it's easy to observe the spectra. And we can get observation. These are the gray dots here. These are the observation of these barium stars with error bars that are like decent error bars. You know, here we are in notation of DEC, the usual notation. So we have ratios relative to solar in logarithm. And you can see that error bars are like 50% or even less, yeah, even at 25% in some plus minus, you know, plus minus 0.1 DEC. So these are fantastic data. And the revolution for us who love these barium stars happened a few years ago when the people in Brazil, they did a program at the ESO telescopes, and they observed 170 barium stars, which has never been done before. Normally we had like 10, maybe 15. And so we have very limited sample, but these people, they observed 160, 170 with the same telescope, analyze them in the same way. So this is the most self-consistent sample. And this is the driving of my work here, that I'm like, yes, finally, we can say something really solid. Same type of star, everything is very is all the same type of information. We're not mixing things up. It's all oranges here, yeah. So I really loved this observation, and I thought we studied them, we look at them. So actually, this is a plot that resemble a plot we have in another paper, but now I want to use them for the Stardust grains, to compare to Stardust grains. Nice. So what is shown here? So at the x-axis is ion over age. So is the metal content of the star, right? So going back, we have lower metallicity stars. Going to the right, we have higher metallicity stars. 0 is solar, as people are probably familiar with this. On the y-axis, it's the cerium over yttrium. So these are two of these wonderfully named elements. Cerium has mass around 140, and yttrium has a mass of 89. So you want to keep this in mind, because it means that cerium is heavier than yttrium. It is more difficult to produce. We need more neutrons to produce it because it's heavier.
Very good.
And as you can see here, very clearly, the data is showing us that lower metallicities produces higher cerium over yttrium.
Yep, that's a trend.
Yes, and the models are doing the same. This was a fantastic result. So that the models are doing, so these lines are the models, and we use two different sets of models here. So Frutti and Monash model, there are two different sets of models. I am a big fan of trying to compare everything possible. So I'm not shy of trying to put more models and see if they agree with each other. So this is one example. So we have stars of mass. The mass is indicated in the legend there, 1.5, 3, and 4. And we can see that overall, the trend that we see in the models and the trend that we see in the data is the same, right? So lower metallicities produce higher cerium over yttrium. So lower metallicities produce heavier elements. I have a reason for this. I can explain if, or this is going into too much details, or you think is interesting to explain why.
It's interesting to explain why.
I think so too. So basically what happens is that when you go to lower metallicities, you have less ion, obviously. Ion is the seed of the neutron captures. Neutron captures start from ion because it's very abundant. There's a lot of ion. It's the first element that start capturing neutron to produce everything that comes later. So what happens is that if we have more neutrons per ion seed, per ion nucleus, we can produce heavier elements because there's less seed to capture the neutrons. So say I get up to yttrium and there's still neutrons, so that yttrium can still capture.
Right.
If I have more ion and the same amount of neutron, then ion capture all the neutrons,
Yep.
and I only get up to yttrium. And then, oops, there's no more neutrons. How do I go to cerium? No way. So this is the reason why. And the fact that the neutron production doesn't change with the metal content. This is a feature of the current models of neutron captures in these stars. That is a very robust feature.
Okay.
So we think we understand these models looking from this plot. And this is I would say, the main feature of these neutron captures in these stars, which impact also the galaxy evolution, for example, as lower metallicity stars produce the heavier elements. And there's a lot of implication about this. But this is, for me, it's interested only in relationship to this plot. So what we did in the bottom panel, we simply decided to check, because this will be relevant for the Stardust, to check how many stars in each metallicity bin have cerium over yttrium above solar or below solar.
Okay.
So looking at the trend up there, it's quite obvious that we find an increasing number of stars as the metallicity increases that have lower than solar cerium over yttrium. This is just a statistical massage of the data, but it's showing the same thing that the top plot shows, but in a more quantitative way. So, and we also give an error bar because we did a proper statistical study about this. Yes. Okay, so why I'm talking about stars and the paper is about Stardust. How do I connect this information to the Stardust? This is the big problem here. And the problem is that you would say, well, why you don't plot here the cerium over yttrium of the Stardust? Just plot that and you have another information there. Right. I can't. I cannot do this because I don't have cerium over yttrium of the Stardust. Okay. Well, I can measure it, but it doesn't tell me something about the nucleosynthesis process. It tells me something about the mineralogy of the Stardust. It's chemistry, it's not nuclear physics anymore. Because the Stardust form from a gas that condenses into solid. And this is chemistry. So, for example, the Stardust I'm looking at is made of silicon and carbon. But this is not because these stars are rich in silicon more than magnesium. It's because this is silicon carbide and its mineralogy is silicon and carbon. So even if I measure the cerium over yttrium in the Stardust, and people do, it doesn't tell me the nucleosynthesis process. It tells me the dust condensation process.
Right. Yes.
It's not what I want to check the nucleosynthesis. That's the main problem here.
I'm with you. Yep.
Yes. So what do I do? What do I have for the Stardust? Maybe we can have a look at table 1. Unfortunately, the table is not a figure, but it was easier because it's a bit of information. So this is what I have from Stardust. Some of the information is obviously not all the information is the one that is relevant here. What I have from Stardust is, this is the last 3 columns, isotopic ratios. So for each element, we have isotopes. So for example, silicon in the column there, yeah, that's 3 stable isotopes, 28, 29, and 30. These stable isotopes, they are all silicon. They behave chemically like silicon. They don't tell me anything, the isotopes, about the dust condensation process. But they tell me about the nucleosynthesis because that's what controls them. So that's the main problem. Stardust is giving me isotopes. stars are giving me elements.
Right.
How do I put them in the same plot? That's what we wanted to do for a long time, and how to find a way to do this. So here I want to show, because the 1, 2, 3, for the fifth column is the one most relevant here. So this is strontium, strontium-88 divided strontium-86. So strontium has 4 stable isotopes, and these 2 are particularly interesting because they are produced by neutron captures. We also have a little complication here, because in the previous plot, I was showing that we represent spectroscopic observation using the DEC notation, the square bracket notation that normally astronomers are familiar with. But astronomers are not normally familiar with this delta little thing that I put in front of that is a different notation, just to make it more complicated.
Of course.
So, of course. Because these come not from astronomy, but from cosmochemistry, geochemistry notation. Because these are the people that work in the lab and use these other symbols. It's another group of people. They speak another language almost. So the delta here is basically the variation relative to solar multiplied by 1000. It's exactly the same as a percent variation, but instead of percent, is multiplied per mil by 1000, just one more zero. So what we see here, for example, 20 means 2% higher than solar.
Yes.
Minus 80 means less than solar by 1.8%. And we and people multiply by this big number because then we can see the number better, basically. Otherwise would be 0.00. Okay, so they want to write them in a plot in a nicer way.
Yep.
Yeah. So what we see here, when we look at the strontium isotopic variation, I see something that's very interesting for me. They change from positive, which means above solar, to negative, which means below solar, when we change the grain size. So the first column is the name of a fraction of a particular fraction sample, and the size is on the second column. So you can see that as the size increases, the strontium 88 divided 86 decreases and goes from above solar to below solar. And so these I am very interested in, because why should that happen? Like, it's a nucleosynthesis effect. It's not a chemistry effect. For chemistry, strontium 88, 86, 87, they're all the same, they're strontium. But when I look at the nucleosynthesis, they can change. And why is this happening? And when we look at the largest grains, the ones I'm interested in, the KJE and KJG fractions, the one around 1 micrometer or a bit higher, they're all negative. They all have negative strontium 88, 86 delta, which means less than solar.
Yes.
So what we did was this. We thought, okay, what do neutron captures predict for cerium over yttrium, which is the stars, versus strontium 88 divided strontium 86, which is the grains?
Okay.
Do we have a way, because we need a way to link these two observables. They are two different observables. So that's what we did, and that's we go to the next figure 2, I think, which is, I think, my favorite figure, the butterfly figure. That's how we ended up calling it.
I can see
because
this.
it ended up being a butterfly.
Yes.
So that's what we did. And this, we can only do models for this, because we want the link between what we observe in the stars, the cerium over yttrium in the x-axis, and what we observe in the grains, which is the strontium ratios on the y-axis.
Very cool. All right.
How can we, yes? Is it?
Yeah, I'm with you.
Okay, just stop me if, yeah, okay. So here, we don't have observations to plot here, unfortunately, because as I'm saying, the grain gives me this and the stars give me that. But I can correlate these using models.
Okay.
Okay, so I said before that I don't trust models. So what am I doing now? You know, like, why? She said that models are uncertain. Why now you're relying on models? Okay, so this is why the first thing we did was this butterfly, and this is the black line. The black line I trust very much because this is not a stellar model, it's a network model. What we did here, we just took solar system composition, and we threw neutrons at it. So the black line only depends on the nuclear properties of the nuclei. We kept a constant temperature, but that doesn't matter too much because neutron captures don't change much with temperature. We gave the neutrons to the material and let it go and see what happens. Okay. And so this one I trust because it's only nuclear physics. There's no stars involved in that, no stellar model, which include a lot of uncertainty. So what happens, we start from 0.00. So you can, if you want, you put the, yeah, that's where we start. Because I said we start with solar composition. We could try other things, but it doesn't really matter. And that's 0.00 because cerium over yttrium solar in square bracket notation is 0. And strontium 8886 in delta notation, the solar is 0. So that's where we start. Yep. What happens? I start giving neutrons. Strontium, you see the mass here. The mass is 88, 86 and 88. Yes. The mass of yttrium is 89. So the first thing that I do is that I reach strontium. I capture neutrons, I reach strontium first. And I see effect on strontium because I start producing strontium 88, which is a neutron magic number. It likes to not capture neutrons. So the first thing I see, the line goes down. But then what happens, I start to also produce yttrium 89, which is just above strontium. So the line goes to the left. Okay. Because I'm producing yttrium as well. There are some little, you know, equilibrium things happening, but typically what's happened, the line is going down to the left to very low cerium over yttrium because I'm building the first S process peak effectively, which is the first magic at strontium 88 and yttrium 89. But then in this model, I do what I want. I keep on feeding it neutrons. Why should I stop? I keep on giving neutrons. And the first thing that happens is that the ratio of 88 and 86 start going up. And then I also produce cerium because the flux is going to the heavier one. Cerium has mass 140. So I keep on giving neutrons. And so my butterflies is turning back and actually is going back to solar. And then it's going to higher cerium over yttrium because I'm producing a lot of cerium. And I get more or less where you are with the line up to the peak there. That's, yeah. And then what happens? Why am I going down and back again? Because I keep on giving neutrons. That's fun. I keep on send more neutrons. So cerium also start capturing neutrons, and I end up producing lead. So I go to the end of the chain, and the line comes back here. Very good. So this is features of nuclear physics, which are quite well determined because the neutron capture cross sections of these isotopes, they're measured in the laboratory. They're not a theory. It's experimental data. So when I throw neutrons at this network of isotopes, there's no other way that they can behave. Yeah, this is, I feel about this robustly, and this is what makes me confident. Okay. Then, yes, so then we look at the models, because then we also have real models. This is not a real stellar model. It was just a play game. It was just a game. But let's look if the models make sense within this framework. So again, we took many different models. Again, these are three different sets of models. Monash is M, and it's the full symbols. Fruity is the open symbols. Then we have some NuGrid models as well that we found in the literature, and we put them all in. Yeah. So for different masses, we connect the metallicity by a line for the same mass. And what we find is that it's all self-consistent. The models are inside the butterfly.
Right.
Because the models, in stellar models, they're dilution. So we cannot be at the extreme of what a nuclear network would give you. We have dilution. So we also plotted some mixing lines there, which has this curved line. And all the model, they sit in between there. There's no way to go out of this butterfly. I bet if someone find me a way to go out of this butterfly, I'll be interested and I challenge it. Okay, so
what a deal.
This is where we stay. Yeah.
What a deal. Very good.
Yes.
Yeah, it's nice.
So now I can try to go back to my previous point. And my previous point was, if you remember, that the large grains from the table have delta strontium 88, 86 lower than solar.
Yes.
Negative. So the grains are below the 0 point. They're all located there in that quadrant, in the bottom left quadrant. That's where the grain are. Well, the grain could be anywhere, but the butterfly is constraining me that if this grain have these lower than solar isotopic ratio, their parent stars must have lower than solar cerium over yttrium.
Okay.
They cannot, because there's no butterfly in the bottom right quadrant. It doesn't exist.
Right.
There's nothing there that can cover that. So this is why we concluded that the grains should come from stars of cerium over yttrium negative.
Yes.
Now, let's go back to figure 1.
Okay.
Because now we've gone a long way and I want to wrap it up back to figure 1. Which one were the stars with negative cerium over yttrium? The ones with metallicity higher than solar. This is observations.
Yeah.
It's not just the models telling me this. The models are telling me also this, but I could actually match the strontium doing other tricks, not changing the metallicity, changing some parameters in my models. But I shouldn't do that. I should change the metallicity. And if I change the metallicity, I can match that, and I can also recover the fact that cerium over yttrium below solar comes from barium star of supersolar metallicity.
Okay.
So this is why we got to the main conclusion of the paper, which is the title of the paper, after all. You know, large grains come from high metallicity AGB stars. And it took a bit of a tour, but yes, so the large grains come from metal-rich AGB stars.
Very good.
The small grains, instead, they are allowed to come from lower metallicity AGB stars, because their strontium over yttrium, their strontium isotopic ratios are positive. So they might be, they are somewhere in the top, yes, they're somewhere in the top of this figure, either the left or the right quadrant. I cannot tell, it's both, it could be both, because both cases are possible.
Okay.
So I am more allowed to go to stars that have lower metallicities. So this is what I was very happy about. This paper, getting some robust conclusion. I think, so there's only 2 more things that I would like to mention, if you think there is time.
There's plenty of time.
So briefly, because I really want the message to be what I just explained. This is my main message for the paper. But there's 2 more things I want to say. One is something that for me is a confirmation of what we are doing. So then we don't shy out of also comparing the Stardust grain data with the models.
Okay.
So this is done in some figures in this paper. We can choose an example. I don't mind which one. We can choose a nickel example. Is an interesting element that is measuring Stardust. Maybe the figure 3 could be already a good one. Yes, it's an example. So this is nickel. Nickel isotopes are measured in the grains. The grain data are the circles with the error bars. The models are the symbols of different types. These are for different masses. The metallicity to the right is solar metal, to the left is solar metallicity, to the right is super solar.
Yes.
And from here, I mean, we don't have strong indication for one case or the other, although we are still happy with what the models do with these. Like we have to select some models. Maybe my favorite would be something like a 3.5 to 4 solar mass stars for both solar and twice solar metallicity. This is an example. There's not much more in this paper because I did a whole detail study in the paper of 2018, which is cited here, where I look at strontium, zirconium, barium. So it's just an example to say that this is still a valid methodology and we still want to compare grains with models. And the last thing that I want to say is still a bit of a problem that we have, and maybe we can, I mean, we can go to the last figure, even if it's, because here the last figure showed that we also looked at the process of dust formation, which is a completely different thing than the nucleosynthesis, because it happens in the outer cool layers. Yes. So we did it with a different code, with the Aton models. So these show some typical feature that increasing the stellar mass, the silicon carbide is the square. So we can just look at the silicon carbide, and one can see that increasing the stellar mass, starting from 1, there's more and more produced because the star is carbon rich. I didn't mention this before, but it's an important condition to form silicon carbide, to have a gas that has more carbon than oxygen. And then there's no more silicon carbide produced after 3.5 solar masses because the stars suffer hot bottom burning. It means that there's proton captures in the envelope, right in the envelope, and convert carbon to oxygen. So the models produce silicon carbide dust that we find in the meteorites. Fantastic. We observe silicon carbide dust around these stars. Perfect. Yes. Everything looks good. But the models predict a size of about 0.1 micrometer, not 1. And this has been a big problem for a long time and still is. Except that now I am kind of able to say that we have to solve this problem at higher than solar metallicity, because this is where I think the large grain come from. But we haven't, like, this is an open problem and it's difficult. So what we found a possible idea here. So basically in these models of dust formation, they are 1D models. They're not 3D, not as complex as one would want to make them, but it's a beginning. And they are connected to the evolution of the star. So they can feel the carbon and oxygen ratio and all that. They're quite sophisticated. But what they do, they always start with the seed dust. So there's nanometer particles already assumed to be there. And people really don't know yet exactly how you go from the gas to these nano seed particles. And you can choose how many seed particles to put. The typical number is a 10 to the minus 13 of the hydrogen atoms. And is a number, but I mean, is this, usually people use this number for every type of dust, every mass, every metallicity is a typical value.
Right.
But so what we did here, the people in Rome, the group that I asked for help with this, they said, well, let's try to make this seed number a bit smaller or a bit bigger.
Okay.
And by doing that, they actually managed, this was the first time I've seen this happening in a quite simple way, to increase the size of the dust. And the reason is that if you have less seeds, they accrete more because they capture more of the molecules that are around.
Okay.
Yeah, so this was one thing that at least is not the final solution or anything. It was a fun, like, let's try something. How do we get bigger grains? So it's still an open problem. I still don't know why stars of higher metallicity should have less seeds.
Yeah.
Or what, maybe, like, you know, like this is, we can try to do some observation of dust around AGB stars, and this is what we discuss in the conclusion as well, though it's difficult because the metallicity itself of AGB stars is difficult to measure, and the dust type is difficult to identify. There's a lot of graphite and carbon dust as well.
Right. Yes.
So, but at least we were trying to push as high. Yes, so this is what we report here. If we decrease the number of seeds, we can increase the grain size. At least it's some light at the end of the tunnel, or just a game, I don't know yet. But it was a fun trying to push it a bit. You know, we just tried to push it and ended up with a very long paper because we kept on tried to push everything to the limits of what we could do at the moment, which was the fun. So I think on my side, I'm quite happy about what I try to convey, my main message and a couple extra things. But what do you think, Frank? Is this a summary?
I think it's awesome. I think
okay.
Very good with that. Well, thank you very much for walking through your lovely article here. And let me ask you to, where do we go from here? Given you've hinted at a couple directions. One is let's say more infrared observations of AGB stars of various metallicities. So, is there upcoming efforts in the next 5 years, maybe with JWST or ALMA?
Yeah.
Are there new observations to do? Are there new laboratory astrophysics things to do on measuring maybe different isotopes in those grains that can help shed some light on cesium and yttrium? And finally, are there other potentially stellar theoretical models that you might believe a little more? I don't know. But sort of where do we go, since you've got several?
Yeah. So this is super exciting.
Yeah, where do we go over, say, the next 5 years?
Yeah. Okay. So of course, I'm not gonna spend too much time on saying that we need more data, and that's obvious, and everybody wants that, and more data of different elements in the same grains. People are starting to do that, so we can train model more strongly. But what I'm really excited about is that, so if there were AGB stars, so stars, evolved stars, but say they are maybe 3 solar mass, so they don't take too long on the main sequence, maybe like less than 1 billion year on the main sequence, or something like that. Yeah. There were metal-rich stars at the time before the sun formed.
Okay.
Can we constrain the age metallicity relationship of the solar neighborhood 4.6 billion years ago?
Right.
This is exciting because we're doing nuclear physics, stellar physics, meteoritic, and we can do Milky Way study with these grains.
Very cool.
And actually, I was very, very excited to see last year a paper by Nissen et al., who looked at about 70 solar type stars, and they did an amazing age metallicity relationship because they did the ages in a super fantastic way. So ages are hard, but they managed to have small error bars. And they found two populations of which the older population at the time of the birth of the sun reached a metallicity higher than solar, which is what I want.
Okay.
But there are different ways to explain this because we are observing this now. So it could be that these stars moved around. So they were not there when the sun formed at the time of the sun form, but they came there from other places. They have their age, but they came from somewhere else. But what I want to say is that those stars must have been there when the sun was born because they gave us these grains. And this has implication on the type of galactic chemical evolution model that you want to use to explain them. So I'm going a long way far, but it's so exciting that I can't really stop here, and we'll have to do this. I'm going to do this next. So using the grain, again, I did this before, but with this new data from stellar observation, this is really something I want to pin down, the connection with the Milky Way, chemical, age metallicity relationship, and the stardust grains. I think this can really tell us something new that come from different perspectives. So sorry, I went a bit off onto another tangent, but this is what I'm really excited about.
All good. Excitement is a good thing. Well, I look forward to, sounds like there's a lot of activity in this field, and I look forward to seeing some of your future works, Maria.
Yes, maybe we can chat about the chemical evolution of the galaxy.
That would be lovely. That would be lovely. I would like that very much.
Yes.
All right. So thank you. And thank you, everyone.
Thank you.
And I hope this made your astronomy day just a little bit better. And we'll see you on the next one. Bye-bye.
Thank you. Bye-bye.